Attendees are in listen-only mode.
Good afternoon, and thank you for joining us today as the National Board of Public Health Examiners presents the second in our series of 5 webinars geared to explaining the Certified in Public Health credential and to help you prepare for the upcoming exam. Each of our sessions will be 2.5 to 3 hours long and include lectures and interactive segments. You may register for the remaining 3 sessions on biostatistics, environmental health, and behavioral and social sciences on the NBPHE website. Today, we are happy to present an epidemiology webinar. Pleased to have Dr. Paul Terry, Associate Professor of the Department of Public Health and Surgery from the College of Education, Health and Human Sciences at the University of Tennessee. Dr. Terry, thank you for joining us today.
Thank you very much. Again, my name is Paul Terry. I'm happy to be here. I wish everyone luck on their exam. This is a review of basic topics covered in the epidemiology section of the exam. And the materials covered, of course, cannot replace a basic epidemiology course. This is just a review. This review will be archived on the NBPHE website under Study Resources. So a basic outline of what we'll be talking about. We'll be going through some definitions and terminology, measures of disease frequency, epidemiologic study design, and I'll have a few questions for you, a little quiz here and there on study designs, causation, how to judge whether an association is causal, and screening for disease. So first, the definition, basic definition of epidemiology is the study of distribution and determinants of health-related states or events in specified populations and the application of this study to control health problems. Now, you'll notice that the word disease is not in this particular definition. It used to be in older versions of epidemiology definitions, but to be honest, we will use the term disease often because that's often what we're looking at as an outcome, and health-related states or events is a mouthful. So, but realize that when we talk about disease, it's not the only outcome that we can have in epidemiology. Even a cure is an outcome in epidemiology, and it's not a disease per se. It's an improvement. So be aware of the fact that people do use disease to mean more generally health-related states or events in specified populations. Now, distribution is highlighted because that's distinguished from determinants. Determinants are more of what might cause a particular outcome. But distribution is more of a descriptive. It's part of descriptive epidemiology, and it brings up several basic questions. For example, how common is this disease?
Dr. Terry,
Yes.
This is Erin. I just want to interrupt you for just one moment. We are still seeing the title slide, and I want to make sure that if you've moved along that we are progressing.
Yes, I have moved along, actually.
Okay.
So I am now on a slide that talks about disease distribution. Are you not able to see that slide?
If we can advance to that slide, please.
Okay, hold on one moment. Some technical difficulties here. Let me do this real quick. I'm gonna change out, and I'm gonna re-switch it back to Dr. Terry.
All right.
Okay, sorry about that, and you should be able to show now.
I will click Show My Screen. And it says attendees still on hold. Should I start broadcast?
Yep, go. Yeah, it's already broadcasting, but
okay. So what screen do you see at this point?
Disease distribution.
We are now on disease distribution.
Ah, good. Thank you. And my apologies. Hopefully we don't have any more glitches. So these are the.
You know.
Oh yeah, it's no problem. Even movie theaters make mistakes once in a while. So how common is the disease or outcome? Who is affected? When does it occur? Where does it occur? I mean, these are just basic questions about disease distribution. And you'll see these questions lead to more questions. For example, is this a causal factor in this disease or outcome? So how common? So there are some basic terms you should be familiar with. Endemic, usual presence of a disease within a given population. Epidemic, occurrence of a disease clearly in excess of normal expectancy in a defined community or region, and pandemic, a worldwide epidemic. So where's the line between endemic and epidemic? For example, people refer to an epidemic of obesity in this country. At some point, at least the way we're viewed from other countries, we may be endemically obese here. So the dividing line between epidemic and endemic is not always clear. Now, when it comes to a rare or sporadic disease, there are definitions. For example, one definition says less than 200,000 people in the United States have, less than 200,000 cases is a rare disease. But the problem with definitions is that you'll find that in some communities it doesn't seem so rare, or in some points in time it doesn't seem so rare. So I use the term rare a little bit carefully. Who is affected? So here are some descriptive epidemiology parameters for people. So these personal characteristics are not a complete list. They're just one of many things that disease can vary on. For example, age and sex, race, ethnicity, education. When it comes to populations, membership can be permanent or transient. A population with a permanent membership is referred to as a fixed or closed population. For example, people experiencing a particular unique event, like being present in Hiroshima, or passengers on a particular airplane, or people enrolled in a specific cohort. If anyone knows of a specific cohort, like the Nurses' Health Study, Physicians' Health Study, Framingham Study, that's a closed cohort. A population with a transient membership is referred to as a dynamic or open cohort. For example, the population of Omaha. Even if year after year the population seems to remain stable, certainly some people are moving in and some people are moving out. That's why it's called a dynamic group or population or cohort. When does it occur? When does disease occur? Well, this is just one example. You can look at malaria and you can look at the efforts that were made and see if the efforts that were made to stem malaria are working over time. This is just one example of annual plague deaths in London. And it also re-emphasizes the point I made about what's a rare disease. It's rare at some time, and it may not be rare at another time. Where does it occur? This is an example you should know about. It's the famous cholera cases in Golden Square area of London, where John Snow linked the Broad Street pump to cholera. And that was really a question of where are these cases occurring? They're occurring around the Broad Street pump. So now some basic measures of morbidity. When we talk about mortality, you'll find that they're the same measures. 4 simple mathematical parameters: counts, ratios, proportions, and rates. So we will distinguish these. A count is the most basic epidemiologic measure. It's basically 1, 2, 3, you're counting. You're counting people. Answers the question, how many people have this disease? It's important to distinguish between incident and prevalent cases as we go through measures of frequency. So if we're counting, are we counting new cases or incident cases? Are we counting existing cases, which may be incident and prevalent? Basically prevalent cases. So here's a basic count over time, deaths in the United States. During the 20th century, you see the number of deaths is increasing. These are in thousands. The numbers of deaths are increasing over time. But does that mean it's more dangerous to live in the United States over time? Well, there's something obviously missing, and the count doesn't have it, and that's a denominator. How many people are in the denominator? How many people are at risk of dying, for example? So we get into ratios. Ratios have numerators on the top usually and denominators on the bottom. So a ratio is one number divided by another, or x over y. And the range of a ratio typically is 0 to infinity. For example, if the denominator is 0, the ratio will be infinity. If the numerator is 0, the ratio will be 0. So X and Y may be related or completely independent. And this is an example of sex of children attending a clinic. So what's the ratio of females to males? If, it could be 3 to 1. For every male, 3 females come in. Now this is also a ratio, females to all children. But you'll notice something different about it. And that is the numerator, females, are contained in the denominator, all children. All children are made up of males and females. Females are part of that. So this is not a typical ratio. It's a type of ratio, proportion. Now, proportion is a ratio in which the numerator is included in the denominator, just like the example we just gave. And the range of this proportion, this type of ratio, is 0 to 1. For example, you can't have more than 100% female in any population, and you can't have less than 0% female in any population. So the range of a proportion is 0 to 1. And it's often expressed as a percentage. For example, among all children who attend a clinic, what proportion was female? A rate, generally speaking, is a quantity per unit of time, and you'll see it used as a synonym sometimes for a proportion, but it's not. A rate, generally speaking, is a quantity per unit of time. Here's some examples. The woman's heart rate was 60 beats per minute. The driver's rate of speed was 60 miles per hour. The man's pay rate was $60 per day. So you see that time is a part of the denominator. This is a count per unit of time, and that's how we're defining rate. For those of you who like formulas, it can be expressed as A over T, where A is the cases, number of cases, new cases actually, and T involves a component of time. And a rate actually varies from 0 to infinity and measures the speed at which things happen. In epidemiology, the speed at which disease occurs. Prevalence. Prevalence is a proportion. It's not a rate. There's no time component in the calculation. It measures the proportion of existing disease in the population at a given time. How many of you have a cold right now? Out of the total amount of people in the audience, how many of you have a cold? So it's a snapshot. It's not asking when you got your cold. It's whether you have a cold. It's existing disease. It's dimensionless, positive number, 0 to 1. And here's a basic formula where number of existing cases divided by the total population. So incidence, as opposed to prevalence, measures the occurrence of new cases in a population at risk over time. And that can be measured as a proportion or a rate. Now that you know about proportions and rates, we can talk a little bit about the most common epidemiologic terms used to describe incidence. And incidence proportion is, well, I call it a risk, but it also goes by other names, incidence, cumulative incidence. It measures the probability or risk of developing disease during a period of observation. And it's a proportion, and so it ranges from 0 to 1. So here, basic formula is risk is the number of new onset cases or events over the population at risk at the beginning of follow-up. So follow-up is when you observe a group of people over time to see what events occur in those people. So you must specify the time period of observation because risk changes with time. For example, a 5-year period under which we're observing mortality or an incidence of disease will be less than a 10-year risk event. And that will be less than a 20-year risk event. So, and you also must specify the population because risk varies across populations. What's true in one country is not true in another country, or even a state, or a region, or a group of people. And that's why we looked at different groups of people before. So here's an example where we're following 2,000 newborns at monthly intervals to measure development of respiratory infections in the first year. Now suppose 50 infants develop respiratory infection in the first year of life. Well, the denominator is the number of people at the beginning of our follow-up who we're following, who are at risk of getting the outcome. And of those, 50 developed new respiratory infections in the first year of life. So 50 divided by 2,000 is 0.25, which is 2.5%. So the risk of developing a respiratory infection in the first year of life in this population, and again it's specifying the time, first year of life, is 2.5%. Now, 2.5 out of 100 is the same as 25 out of 1,000, or 250 out of 10,000. So whatever way to express it that is the most easiest to comprehend is possible. So in this, we could say 25 out of 1,000 infants in this population, or 1 in 40, will develop infection in the first year of life. Incidence rate measures how rapidly new cases develop during a specified time period. Again, it's new cases per person time. And you can also hear it referred to as incidence in a very general way, or incidence density, or rate. Basic formula: the number of new onset cases divided by the person time at risk during study period. So person time accounts for all the time each person is in the population at risk. The length of time for each person is called person time. The sum of person times is called the total person time at risk for the population, and that's what goes in the denominator of these rates. Now, of course, there's an assumption here, and it's maybe difficult to wrap your mind around, but you can reach, for example, 1,000 person years in many different ways. You can follow 100 people for 10 years. You can follow 1,000 people for 1 year. Or I guess you can follow 10,000 people for 1/10 of a year and get 1,000 person years. And this assumes the rate is constant over different periods of time. So be aware of that assumption. Here's a basic, simple cohort study I created with line drawings. As you can see, there are 5 people being followed forward in time for 12 months. There's only one event, which is signified by a red X at 6 months. So let's figure out the person time. As I said, it's a sum of all the person times experienced in your cohort during follow-up. So you'll notice that persons number 1, 3, 4, and 5 have all gone 12 months without either leaving the cohort or leaving the follow-up or getting the outcome. So they each contribute a full year. But person number 2 got the outcome after 6 months. At that point, we stop following that person. That person is no longer being followed for this outcome. Why? Because this person already has it. They are no longer at risk for a new case of this outcome. So what's the total person time? It's 4 times 12 plus 6, or 54 months, or 4.5 years. So one new case divided by 4.5 person years is 0.22 cases per person per year. Can we say this in terms of months, person months? Of course we can. One new case in 54 person months is 0.0185 cases per person per month, or per person month. We could do it in person seconds. There'd be no point to it, but we could do it. Or person centuries. Now, a word on the relationship between incidence, prevalence, and duration. There was a formula going back a long time in basic texts in epidemiology. Prevalence equals incidence times duration. And here's a picture of why that occurs. Incidence, imagine the prevalence is the pool of people. It's like a pool of people in the area that you're looking at who have a certain disease, existing disease. Now, entering this pool are people who get new cases of that disease or incidence, and exiting the pool are people who die of their disease or are cured from their disease. Either way, they no longer have the disease. So prevalence is a measure, is a product of incidence and duration. So if somebody says, oh, the prevalence of disease X is increasing, maybe disease X could be AIDS. There are more people existing with AIDS. The prevalence is increasing. Is that necessarily a bad thing? Well, it depends on how you look at it. It may not be that the incidence of this outcome is increasing. It may be that the survivability is increasing. Measures of mortality, very similar to measures of morbidity. Measures the occurrence of death, can be measured as a proportion or a rate, just like disease incidence. You have the risk of death, risk of disease, rate of death, rate of disease. The statistical calculations for risks and rates for mortality are similar to those for disease morbidity. Now, case fatality rate, this is not a rate. It's called a rate, but it has no unit of time the way a rate does. It's actually a proportion. The proportion of deaths from a specific illness. So a case fatality rate is the number of deaths from an illness divided by the number of people with that illness. So what percentage of people diagnosed as having a disease die within a certain time after diagnosis? The better the cure, the better the treatment, the lower the case fatality rate. Certain infections like TB had a much higher case fatality rate before we developed antibiotics, for example. So case fatality is a measure of the severity of the disease and also the efficacy of the treatment. And it can be used to measure benefits of a new therapy. As the therapy improves, as I mentioned before, the case fatality rate would be expected to decline. And